Most reactions occur in a series of steps, not just one step, and this series of steps is called the mechanism. In most mechanisms, one step is slower than the other, and this is called the rate determining step. And the rate determining step determines the rate at which the overall reaction occurs. The other steps are fast by comparison. So from a combination of experimental data and chemical intuition, we can propose a mechanism by which a reaction occurs. The rate law tells you the reactants in the slow step. So in this example here, the rate law is K times NO2 squared, so that means there are 2 NO2s in the slow step. And so the following proposed two-step mechanism is consistent with the observed rate law expression for this particular reaction. Since the rate law was NO2 squared, that means my slow step has 2 NO2s in it. And I know the overall reaction is this. And so the rest I can kind of fill in. NO2 plus NO2, one possibility is that they form N2O4. So this is the slow step. And then we're going to have a fast step down here. Now N2O4 does not occur in the final reaction, so it's going to be an intermediate. It's going to be formed in the first step and used up in the second step. You will also notice that I need to have carbon monoxide as a reactant, so I'm going to add carbon monoxide as a reactant in the fast step. And I need to form one NO2 because one of the NO2s has to cancel out. I also need to form NO plus CO2. So make sure that fast step works out stoichiometrically. That is, the atoms on both sides of the equation have to balance. So it's possible for N2O4 plus CO to form NO2 plus NO plus CO2. So N2O4 is called an intermediate. It's formed in the first step and used up in the second step. And the NO2s cancel out as well. That leaves us with the overall reaction. So this is one possible mechanism for this particular reaction. Now, let's say NO3 has been identified as a short-lived intermediate for this same reaction. We can actually propose another mechanism. We know the rate law, so we know the reactants in the slow step. We also know the overall reaction. But if I know NO3 is an intermediate, that means my other product in this slow step has to be NO stoichiometrically. This is still the slow step because that's the rate law. In the fast step, NO3 is used up because it's an intermediate. I also need to react carbon monoxide because that's in my final. If I put NO3 plus CO, I have to use up one of the NO2s, and I also need to form CO2. And stoichiometrically that works out. NO3 plus CO can form NO2 plus CO2. One of the NO2s will cancel out. NO3 is an intermediate. It cancels out, and we're left with the overall reaction. So, as long as the mechanism is consistent with the rate law expression and the steps add to give the overall equation, we are good when we propose a mechanism. So we've shown that the slow step of a multi-step mechanism determines the experimentally observed rate of reaction. When the slow step is the first step, the experimentally determined rate law is just the rate law for the first step. But sometimes the rate determining step, the slow step, is not the first step. Let's look at this example chemical reaction for the overall reaction. 2ClO2 plus F2 forms 2ClO2F. Suppose that this reaction goes by the following mechanism. It's a three-step mechanism. First step, second step, third step. You notice that the first step is reversible. So we can write the rate for the forward first step, and it would look like this. We would use K1 times the reactants, which would be ClO2 times F2. There's also a reverse reaction for step 1, and we can write the reverse reaction for step 1 using K2 times the reactant on the reverse step, which would be ClO2F2. And then we know K3, so we could write the rate for the second step using K3 and plugging in the reactant in the second step, which would be ClO2F2. Now, the rate of the overall reaction is limited by the rate of the second step, which is right here, because that is the slow step, I'm told, in the mechanism. Well, ClO2F2 is an intermediate, and it's not normal practice to write the rate law for an overall reaction in terms of an intermediate. So we need to eliminate the intermediate from the rate law expression. Now, if you look at the first step of this mechanism, it's reversible. A point is reached in the first step where the forward reaction is equal to the reverse reaction. And so we can set the forward rate on step 1 equal to the reverse rate on step 1, and I gave you those rate expressions on the previous slide. So those are going to be equal to each other at some point. We can solve for this intermediate, and then we can do some substitutions, because once we get the intermediate and we substitute back into the rate law, we get a rate law that looks like this. And this is the correct rate law, because no longer are we in terms of an intermediate, we're in terms of reactants. So if the slow step is not the first step, we need to make some appropriate substitutions in order to get rid of any intermediates that may occur. The rate law for the overall reaction has to include reactants from the overall reaction.